Let's see if we can make this video before the pizza is done. Solving inequalities, graphing on a number line, comparing it to a two-dimensional graph. First one, x plus 1 is less than 10. We can subtract 1 from both sides. We have x is less than 9. On a number line, simple enough. We'll put 9 here. I like to put 0 as well as a second point, just as a reference. You can use anything, but 0 is handy. This is strictly less than 9, so we have an open circle. And this is all the numbers that are less than 9, so we're going this direction. You can fill this in as dark as you like, just as long as it is clear that which direction you're going. Writing this in interval notation, the left-handmost and the right-handmost numbers, the left-handmost, it doesn't stop, so we're going to negative infinity. And the right-hand highest number is 9, or almost to 9. It doesn't include 9, so we're going to be an open parenthesis on the right as well. So it goes, all the numbers from negative infinity to 9, up to 9, not including it, are less than 9. So that's our graphing on a number line and in interval notation. All right, second example, when we are looking at an absolute value. I remember this creates two different problems for us. Since the absolute value is by itself on one side of the inequality symbol, we don't have to do anything before we split this up into two parts. The positive side and the negative side. So we have the positive side, 7x plus 2. Everything in here, the whole thing is positive, is greater than 10. And the negative side, where this whole thing could be negative. Negative 7x plus 2, or the opposite of the argument, is greater than 10. We want to look at both cases. So here we're just going to solve each inequality, subtract 2 from both sides, and then we're going to divide by 7. So we have 7x is greater than 8, divide by 7 on both sides. We have x is greater than 8 over 7, or 8 sevenths. All right, well, let's do the alternate sides. We have negative 7x minus 2 is greater than 10 when we distribute the negative. Add 2 to both sides, we'll have negative 7x is greater than 12. And we'll divide by negative 7, so x is greater than negative 12 over 7. But when we divide or multiply by a negative, we need to switch the direction of the inequality. So this is no longer greater than, it is now a less than, because we divided by that negative. So we'll have x is less than negative 12 over 7. On a number line, we have negative and a positive. Don't really care how far apart they are, just want to make sure that one is to the left of the other, or one is to the right of the other. The negatives go on the left, positives go on the right in this case. That is a strictly greater than, so we're going to have open circles in both places. We're going to look at each one of these. X is greater than 8 sevenths. Well, greater than, that's to the right. All the numbers greater than are going to be to the right of that 8 sevenths. And x is less than negative 12 over 7. Well, it's that direction. So we're looking at both of these cases as values that would satisfy the original inequality. Now let's look at this in a two-dimensional graph. First off, the x plus 1 less than 10. If we were to graph this, we have, let's say it's y is equal to x plus 1 and y is equal to 10. Graphing this, we have 10 right here. Let me switch colors again. 10 is right there. X plus 1, up 1, slope of 1. Where is x plus 1 less than 10? Well, 10 is right here. Where is it less than? Well, it is less than, here's our point of intersection. The x plus 1 is less than the 10 where it's below it. So it is, in all of these x values, is it less than that? Well, this is a number line. This is 9 right here. It doesn't include that because it's strictly less than, but it's the same thing as our number line here, and it just continues to go on. Looking at our absolute value problem, if we look at it graphically, we have y equals absolute value of 7x plus 2, and then y equals 10. We're looking at the two equations again. Let's go ahead and graph this below, where we can rewrite this. Let's rewrite this very quickly as absolute value of 7 times x plus 2/7. I'm just factoring out a 7. Let's see why, because this is going to be shifting to the left 2/7, and it's going to be 7 times as steep as our parent function. If we factor that out, we'll get our shift and our stretch. So let's go ahead and graph this. XY, again we have our y equals 10, and then absolute value of, let's see, shifted to the left 2/7, right about there, and then it's much steeper. It's looking like that. We want to know where this absolute value function is greater than 10. Well, it's greater than 10 exactly in here to here. It's greater than this direction and greater than that direction. It's greater than 10. It sits above that in our XY plane. And that's what we have. This was our 8/7, and this was our -12/7. So physically, or graphically, on this graph, where the absolute value function is greater than 10, absolute value function is greater than 10, is in these locations, and we represent that on our number line. Interval notation, let's break that out. Again, we're going from -infinity to -12/7. We're not including that, but we're unioning that with 8/7 to positive a infinity. That's our interval notation for the solution of this inequality. Let's look at a quadratic now. X squared plus 2x is greater than or equal to 3. In this case, it's a quadratic, so we're going to want to find the roots. All of our important points are going to be roots. So we're going to set this equal to 0, or in the inequality, it's going to be greater than or equal to 0. So we're going to subtract 3 from both sides. So that's x squared plus 2x minus 3 is greater than or equal to 0. At this point, we would want to factor it. This can be easily factored into x minus 1 times x plus 3 is greater than or equal to 0. We'll set each one of these factors equal to 0, which would give us x minus 1 is greater than or equal to 0, and x plus 3 greater than or equal to 0. So x is greater than or equal to 1, and x is greater than or equal to -3. On our number line, -3, +1, it's greater than or equal to, so we have a closed circle. And on a quadratic, we can't just say it's greater than 1, so it's to the right, and it's greater than -3, so it's to the right. We have two of them to the right. Anytime we have a quadratic, we have to use test points. What are some good test points? Well, we have we have 3 different areas broken up by the -3 and the 1. We have from -infinity to -3, from -3 to 1, and then from 1 to positive infinity. We need to have 3 test numbers to plug in to see if it is indeed x squared plus 2x greater than or equal to 3. So I'm going to pick some numbers that might be simple to use. 10. I can multiply and add, subtract. Oh, there's the pizza. It's done. I better hurry on this. Let's test out -10. We'll test out 0, and we'll test out 2. Well, if I plug in -10, that's 100 minus 20. Is that greater than or equal to 3? Well, 100 minus 20, that's 80, is greater than 3. By gosh, yes, that is. I'm going to put a plus there, or you can put a T for true. But plus, yes, that's true. Plug in 0. Well, 0 plus 0, is that greater than or equal to 3? No, it's not. So that fails. Plug in the 2. That's 2 squared is 4, plus 2 times 2 is 4. Is that greater than or equal to 3? Yes, it is, so that's a positive there. So that tells us that it does not, the values between -3 and 1 do not satisfy this inequality, but the values less than -3 or greater than 1 do satisfy this inequality. So we are looking at that direction, and that direction, writing this in interval notation, -infinity to -3, including the -3, union with, including the 1 to positive infinity. That's solving it and writing it on there. Now, if we look at this graphically, we have x squared plus 2x greater than or equal to 3. Let's use the second form, this one, to look at the graph, which is a parabola. Leading coefficient is positive. It opens upward. It crosses at +1 and -3. We're asking ourselves, when is this greater than or equal to 0? Well, it's greater than or equal to 0 in this area and this area. So graphically, the function x squared plus 2x minus 3 is greater than or equal to 0 in these areas when it's here and here, but not below 0, because that would be less than. All right, let's look at a couple more problems. And now, first, we'll do one more problem, but let's look at the values here. Looking at these test points, why are we plugging those in? What impact does that have? And is there a faster way? Yes, there is. Looking at multiplicity, what if we factored out a polynomial and we get this string of factors where the roots are going to be 0, +1, +1, -5, +4, +5. Now, when we first look at this, we have a multiplicity here of 2. 2 of these are the same. Now, the degree of this polynomial is 1, 2, 3, 4, 5, 6. This came from some x to the 6th plus some other monstrosity. So the degree was 6. We're going to have 6 zeros or roots. But the leading coefficient, again, is positive. What does that tell us? Well, that tells us that this is doing something here, but it's the left-hand limit and the right-hand limit. The end behaviors are both positive. But we have, of our unique roots, we have just 5. So on our number line, we're going to have our -5, our -4, we have 0, we have 1, and we have 5. Now there are 2 of them at 1, but we can only put one time on this. Now these are going to typically alternate, but unless positive, negative, or right or wrong, true or false, if we take test points, say like -10, -4.5, -1, 1/2, 2, and 10, we can take some test points and plug it into this large polynomial and see if that is greater than or equal to 0. But if we know that this is positive on this left behavior, and we're looking for it to be when it's greater than or equal to 0, greater than or equal to 0 is when it's positive. So this is going to be a yes. And we know it's going to end up positive on the right side, so we know this is going to be the yes. So we just have to determine what's going on in between here. Well, pay attention that when we have, or recall, when we have a multiplicity there, the parabola, or the quadratic, this isn't a quadratic, but this function just kisses the x-axis at this point. It just touches it there. It is, for blow-up version, it may be doing something crazy here, but it's just touching right here, and it's not crossing. It's just kissing that. And so we'll take that into consideration. At 1, it's just kissing that. So this is going to alternate to negative here. It's just kissing it so it stays negative. Then it's going back to positive, back to negative, because there are no other repeated roots. And this is we could write this up from negative infinity to negative 5, skip over this section, we're going to include this section, skip over 0 to 5, we don't even mention 1. Well, we do have to mention 1 because 1 is a solution to this. 1 is included because if we plug 1 in here, it is going to be 0, or it is going to be greater than or equal to 0. So because it is included, 1 will be included in that. All right, let's look at a quadratic with an absolute value function. And my lovely bride pulled out the pizza, so we're good on the oven. Crisis averted. I know you were all worried about that. All right, let's take a look at our last problem. Again, we have to make sure that the absolute value bar is, our symbols is separate from the rest of it, and it is right now, so we can break this up into two problems. X squared less than or equal to 4x minus 3, and x squared less than or equal to the opposite of 4x minus 3. We'll go ahead and distribute that to negative 4x plus 3. We're going to solve each one of these as is our norm. All right, solving these. Let's get everything to one side and set it equal to 0 on both of those, and then we can factor it. Long story short, we have x squared minus 4x plus 3 less than or equal to 0. This does factor into x minus 3 and x minus 1 greater than or equal to 0. So we have x is less than or equal to 3, x is less than or equal to 1. Now, not necessarily. These are just points that we are going to plug into our line, our number line, and then check the intervals between them. Let's look at the right one. Let's move it all to the left. X squared plus 4x minus 3 less than or equal to 0. This is prime. We can't factor this. We can use the quadratic formula or completing the square. Let's use completing the square, frankly, because I've already done it, and I have notes off to the side that I'm just copying down. So we have x squared plus 4x, half of 4, so side note, half of 4, and we're going to square that. So that's 2 squared, which is 4. We're going to add and subtract 4 to this. So we're going to add 4 and subtract 4, which doesn't change the value of the whole thing. This plus 4 and minus 4 comes from that little side work that we did. So, but that allows us to take this whole thing and factor it. That is a perfect square trinomial. So we'll have x plus this 2 quantity squared, and then minus 4 and minus 3 is minus 7, less than or equal to 0. Here we can solve for x. We'll get the 7 over to the one side, take the square root, and then subtract it 2. So we'll have x plus 2 quantity squared, less than or equal to 7, take the square root, x plus 2, less than or equal to, plus or minus, square root of 7, subtract the 2, x is less than or equal to negative 2 plus or minus square root of 7. So we have 4 items here. We have 3, we have 1, we have negative 2 plus the square root of 7, and negative 2 minus the square root of 7. Let's make a number line. We have 1, we have 3, negative 2 minus the square root of 7. That's approximately negative 4.6. And we have negative 2 plus the square root of 7 is approximately 0.6. I'm not concerned about the spacing as long as we have the order correct. Looking at test points. Let's choose some easier numbers. Negative 10. We can choose 0. We can choose 3/4 is between the two. We can choose 2, and we can choose 5. We plug these numbers into our original function, the x squared less than or equal to 4x minus 3, the absolute value of that. We're going to plug those test values in to each one, and we're going to see that negative 10 fails that. We're going to see that 0 does satisfy the original inequality. That 3/4 fails 2 passes and 5 fails if when we plug 5 into the original inequality. Again, let's look to see what's going on here. It's 5 squared less than or equal to 4 times 5 minus 3. This is what we're asking ourselves when we plug a 5 in. Is 25 less than or equal to 5 minus 3 is 2. 2 times 4 is 8. Absolute value of 8. Is 25 less than or equal to 8? No, it's not. It's not, so that's why it fails. So we can look at, so let's go ahead and graph this. Let's write this up in our interval notation. We're going from -2 minus the square root of 7 up to -2 plus the square root of 7. And it is less than or equal to, so we are including both of those. We're going to union that from 1 to 3. That's all there is to it. If we were to graph this, we'll end with graphing this very quickly. If we were to graph the two of them, we'd have x squared. Let's see, this is our x squared, and we're looking at our absolute value of 4x minus 3. Let's rewrite that as factor out of 4. We have x minus 3/4. So when we this is going to be shifted to the right, 3/4, right there, and it's going to be 4 times as steep. So it's looking something like this. And we have some points of inflection or interest, which are about right here, and not drawn perfectly, but we have an intersection there, and then somewhere out here we have another intersection. And we see that where is x squared less than? Where is the orange one less than or lower than the pink one? Well, all through here. Oh, the orange one is greater than in this area, but it's less than here, and then it goes back greater than again. And so this is our interval that we see on our number line and our interval notation and our graph.